Hi there. So let's address the practical part of the lifting line theory method. So in the lectures we talk about the theory, also with Professor Bataro. You address this theory, and at the end of the exercise you have the solve exercise. So this is a classical textbook example. Okay, the origins of this case is a paper. Okay, it's all one but it's still valid, and you have it in the material that you downloaded. Okay, this is the paper and this is the name. So as you go, if you go into your material, okay, and should be here papers, and you will find many papers, but you need to look for this one. Okay, no, this one, but there are many papers with different cases. So this is here we have the description of this wind. Okay, so this is a comparison of experimental results and also calculated using this LLT method. In this case it is implemented in this paper, a nonlinear one that takes viscous effect. Okay, so let's see the steps, how it's done. So here in your lectures notes you have all the steps. Okay, the geometry. So remember that it's very important defining the geometry and knowing the characteristics like the whole area, aspect ratio, everything. So that is just a little bit of geometry. Okay, also remember that we need to know the 2D values. Okay, the slopes, but also the zero lift angle of attack, okay, which in this case is minus 1.2. Okay, so that is calculated in Airfoil. Later we're going to see that XFLR5 calculated that automatic, and we have all that information available. As soon as we define the geometry, and also we have this 2D data of the airfoil, we just solve the monoplane equation. Okay, so we divide the wind in different stations. In this case here, in this work example, is divided in 4 stations. Okay, so each station you develop this equation. Okay, and then you compute all these coefficients. The end, all remember that we're interested in solving for A1, A3, or A5, or 7. So at the end, all the information is contained here. So as you get here, you can compute CL in this way. Okay, so here, look at that. We're using, in this example, is using 4 just for a station. Probably is a little bit low. Probably is the minimum that you can use. It's not very accurate, but it will give you a good value. But it's better to use something about 10 or 20, but don't go values 100 is not necessarily. And then also, so here you see the comparison of the theory and then the experimental results. So it's a very good agreement, okay? And also the lift distribution. So also in the material, I show you that you have there this Excel worksheet. So here you have all the equations that are in play. So this is basically, this case that you have there is the Bertin. Okay, this case, the Bertin wind, or probably the civils. Okay, it's very defined as the civil case. You have the paper there. So here we have this definition. So remember that in the monoplane equation, you have 2 contributions. You have the wake model, the one that we add that correction due to the downwash, the 3D effects. And then here you have the section model. You put everything together and you get to this discrete equation. So here, this equation that we add, we solved it using sine series. Okay, so this integral there, we put sine series and we can solve that. So what we have here is that this is the geometrical definition. So look at you have some comments here. Okay, so we're going to redo it in Excel. Then we move to XFLR5. So you define your aspect ratio, taper ratio. Okay, then the angle of attack. So this exercise is done. The one in lectures you have is done at 4 degrees. Okay, so see that we assemble, we give all the geometry. Okay, so B, remember for us, is the tip to tip span. Here B2 is half the semi span. You have all that information here available, and then we have the tip at the core at the rod and tip. Okay, and the number of span wise extensions that we're using for. So basically what we need to do is that we subdivide the wind like this. Okay, so in this case we have 4 stations. So if you go back also here, you will see that you have this angle here. This angle is just corresponds to this. Okay, so kind of a conformal mapping. So you define an angle and then you just find the distance. Okay, you can also give the distance. So this is done a little bit now historical. Now everything, all these methods were associated also with some conformal mapping, so people like to keep like that. So you reduce the angle, you will have more stations. So the idea is that this angle, you have this distance, and then you measure and you put it there. So for each of those extensions, you define the angle. Remember that it's in radians, and then you compute your distance. So this is the complete wind or half the wind. Then you compute the core. Okay, so for each of these distance that you have, okay, so in this case, okay, we're measured like this, half wind. We compute the core. Okay, so here you have the equation. Okay, and this is the equation there. Then we start to compute the series. Okay, so in the equation, in the monoplane equations, you go back, you will see that you have a series of sines functions that we're computing here. Okay, so this summation here corresponds to the number of stations. So the absolute minimum that you need to add is 4. Probably it's too low, but for this working, this is a hand working example, we can do it. So see that now you compute all your functions. Then you have mu. Remember in this one, you are adding all the airfoil geometry, so will correspond to this here. So all the airfoil information you added, you compute it in this way. I just want to point out here that I'm using S. S is half semi-span. Probably in your lectures notes, I think here you have 4B. So S is what is equal to B half, so it's 4B. So I like to work in that way. And you have all those coefficients. After having all those coefficients, you go and you assemble your linear system. Okay, this is your linear system. So you compute everything. Okay, so this is simple, easy algebra. So as you see, you can program this really easy using MATLAB, Python, whatever. It's just a for loop. And then you assemble your system. You have your coefficients. Okay, so you have here A and B. And we want to solve for X, which are the coefficients, A1, 3, 5, 7. So we are only getting here the odd coefficients because we're working with a symmetric distribution. We can also work with a symmetric. For instance, you have ailerons and stuff like that. You will add also the even contribution, even or not. It's a little bit more, it requires a little bit more algebra, but pretty much the same idea. Okay, but for the purpose of designing the wind, we're interested in using the symmetric contribution, as we have also a symmetric wind. Might happen that you have an asymmetric wind, so you should consider that. So here we solve by simple matrix inversion, and then we get all the coefficients. Okay, so as you recall from your lectures now, that in these coefficients, 4 sections, 4 coefficients, you have all the information contained. So see that you go and look at CL, computing in this way. So as you look at your lecture notes, okay, you will see here the results. Okay, we have it here, then all the other coefficients computed in the same way. Again, also, you can go to the paper. Okay, this base wind that we're using is this one. So we are solving for exactly the same case. This is the airfoil. Okay, we know all the characteristics of this airfoil, the slopes, and also the alpha L0. Washout is 0. So as you go here, you will get the value. You will see that the value is a little bit higher, okay, because here we're in the case there are more stations, more accurate, but we are there. Then see the induced. So remember that this is a potential method. We don't have any viscous correction, no viscous information. So we only can compute the induced drag, but depends as we live. Okay, so we compute it in this way. If you want to compute the total drag, you will need to add CD0. Okay, so you can go to tables or previous experience and you can get an idea what is the CD0 of this one. Okay, you can compute the slope of here, or this case like this. Okay, and then the final part, and remember that here in the induced drag you have this coefficient delta, okay, that depends on the rest of the coefficients. Okay, so delta is computed like this. So we use A1 just to compute CL, and then to compute delta, okay, the induced drag factor, you use all the other coefficients. You compute it, you put it here, and you get your value. So we have here CL, CDI. So these are non-dimensional values. Now we can go to the practical part. We want to design this win for a given condition. So we know that we can compute lift in this way. So we know all the information, okay? You have CL, just compute it, just put the values and you can get it. So for instance, in this example, look at that. If our target weight is 400 newtons, kind of 400 kilos, so what velocity you and for this angle of attack, what velocity you should fly to produce the minimum lift? Okay, that is our idea, designing a wing to stay aloft. So it's telling us that 77 meters per second. Okay, so at this point, this information you pass to the guys designing the power plant. Okay, so you know your velocity, you know also the drag of this wing or the whole configuration, and then thrust needs to be equal to drag, and then the guys will design the engine to produce that power. But we're interested in lift. Okay, so also you have density. So remember, density changes with altitude. So for instance, you go higher, okay, maybe your density will go to 1, and see that you produce less lift. You will need to correct by increasing velocity to 85 in this case, and then you have your lift. You can also increase your angle of attack. So for instance, in this case, we're working at 4. Okay, so let's go, for instance, 1 degree, clear, okay, that it will be lower the lift. Okay, let me go back to 1225, okay, sea level, and see that it's half. So to produce the required lift, I need to increase velocity. Okay, so if I go at 120, there we are. Okay, this is the minimum lift that we need to stay aloft. So as you see, very simple method, 4 sections, and even you can use this Excel worksheet to design any wing, okay, within the restrictions of this theory. Okay, so we mentioned that there are many restrictions, but also there are restrictions. But if you stay low speed subsonic, it works wonderful. Okay, so this case here that I show you, okay, was this civil case. But also, okay, let me go back and let me set up this worksheet to the original state. Okay, let me do a few undos here. Okay, so the original state and 1.5. Okay, so we're there. So let's address another. Okay, before that one, let's also see how to set up this case in XFLR5. So you launch the program, okay, and you're going to get that window. Let me close here, so just to show you that when you launch the program, okay, you're going to get this white window. Okay, here in XFLR5 you have also Airfoil included and the model for 3D design. So basically what we want to do, okay, is that we want to design that exactly the same example that we just saw, the civils example, which is this one. Okay, so there you have all the geometrical characteristics. Okay, this is a little bit geometry, how to design this. I'm not going into details, but just to show you also in the material that you download, you should have this case included. Okay, so there is this case data files. No, sorry, it is this one. You have this file, and then there you are going to have civil wins, and you have already the solution. So I'm going to open civils 1. Okay, so as you go to model, open the project, and opening civils win 1, and here I already did the whole definition for you. Okay, later you can reproduce this, but here you see that you have exactly the same win as the paper. Okay, so here you have different buttons for different things that you want to see. So here we're in airplane view, we're seeing the airplane. You go here, you have all the polars. Here you have the span-wise distribution if you want to see that information. Okay, so see that I click there, I get access to that. So here, since I'm not working, okay, and these two that you have here is for stability, and this one is not used. Okay, so we're just interested in this tree. So see that we're running the case. So it's like running the case. So remember that here we're taking to the information. So it's very important that we need to generate. So if you go into module, see that in module you also have access to Airfoil direct analysis. Okay, so in this case, what we did is that we went to this model and see that we run the case for different Reynolds numbers. So this wing has taper ratio, so each section will see a different Reynolds number. Okay, so according, we have design velocity here, we compute, we do some corrections and iterations, and we compute all these Reynolds numbers. Okay, so if you have a rectangular wing, you know that it's uniform, but in this case, different Reynolds numbers. So we need to compute, okay, all the Reynolds, and we run the case. So in this case, XFLR5 is non-linear. It takes the viscous data as well. If I want, we can disable that one, but it doesn't change anything. It runs the same. So it's better to run also viscous to get that information. So see that here we have two airfoils, and basically we cover a lot of Reynolds numbers to be sure that we're in there. My advice when you are doing these studies, later I'm just showing you the case setup. Later we're going to set up everything. Okay, do the increments in steps of 100,000. Okay, 1 million, 1.1, 1.2, and so on. Okay, because what it's doing, the software is interpolating the solution from section to section. So you go and look back at the division by sections. Basically, you have information here, and then you linearly interpolate it from here to here to here, and so on. Okay, so that is what is done. That's why we need to cover now all those Reynolds. So after we do the 2D runs, you can put all the profiles. You go back to Wing Design here. Okay, so in Wing Design, you can design your airplane here. Okay, current. So you go define new plane, and you can define everything. We already have a plane here, so we go into current plane, and you can modify it. In this case, we only have a wing. We don't have elevator, fin, or fuselage. So just the wing. We go here, edit wing, and see that you enter now in this new window, and here's where you do the definition of the geometry. So when you are defining things here, you are just defining one wing. Okay, so be careful that you have your geometrical data. Okay, here is how well, this is the correct one. So if you have this span, you divide it by 2. Okay, so you simply give that information. Okay, so see that we go from here to here. Then we have the core information also. So in the problem definition, you have the core, give the core tip and root, and then the offset. This is to control. Again, this is just geometry. So this is to control the swept back angle. Okay, this angle here. So in this case is leading edge, and just on geometry, this is offset. This is an actual distance. Okay, this is not angle. So if you go 0.2, okay, or 1, you give more sweat. So remember that the LLT doesn't see this effect. Even the non-linear doesn't see this effect. To solve for this, we need to use the vortex method or the full panel method. But in our case, also we saw that we're just interested in that for high speed. We're not in high speed. So here we're keeping the original design, and then diagonal. This is the incidence angle of the wing. Okay, this is not the angle of attack. Be careful. This is the design angle. No, this is this is the angle for the stability. Okay, you define this one. So also for us, we have seen that this will change a little bit the lift, but it's not a problem. And as well, the LLT is kind of this angle doesn't modify the output of the LLT. And then this is the twist. Okay, so this is the actual geometrical twist of the wing. Okay, you are not defining here angle of attack. This is geometrical twist. So you put here, for instance, 2, and here -6, and see that you have your twist, and this is how you control it. So for instance, if you're designing a wing and you want to have an incidence angle or settling angle of the wing, that is the structural angle, the fixed angle, you put it here 2 or whatever you want, and you control that. Okay, this is not angle of attack. This is your structural angle that, okay, you cannot change on fly. You fly, you change your angle of attack. Okay, so our standard original definition of the case that we're solving for the for 0, and then here you add your airfoil. So remember that previously we run, and here you access that information. Okay, so for instance, we have also the NACA information. You can select it with no problem. So see that I go here, and now we are adding aerodynamic twist. Okay, so at the root that you have this airfoil. At the tip, you have this airfoil, and all the information that you run in XFLR, it is contained here automatically. And then the software will do just the interpolation and solve the problem. Okay, so let me go back here like this, and that's all. Okay, after you are satisfied with this one, with this definition, you can add more sections. So we have here just this one to define, but you can add more sections. You save, okay, okay, and then you are ready to run. Okay, so to run the case, remember that you run like in 2D. You need to set few angles. So here we're not interested in going high. We just want to be in the linear part. So usually -4, 8, -4, 8, or 10, it is okay. You run with for these values, and voila, here you go, your solution. As you see, super fast. You can run many computations fast. I want to point out that this is non-linear. We have installed, so this method can compute CL max. You use a fully potential linear method that you cannot compute the stall. We talk about the critical section method. Okay, you can use that one. For the moment, we're not interested in that. So as you go here, just in a little bit, you will see that at 4, you have a value something about 0.48, whatever. Okay, a little bit 49. So see that is pretty much accurate, the Excel value. Okay, so you have all your information. Okay, so remember that here in graph, you can choose different configurations. Okay, so you can choose all for graph, okay, to graph, or single for graph. Okay, so if you put all, you get this. I like to use 4 graph like this. And then is you right click in each graph, you can choose what information you want to see. So see that here we're looking at the induced drag information. So this is a polar induced drag CL. Okay, recall how it's computed, okay, and recall that it's shifted a little bit, is the curve to it. So now let's change that one. Right click and go here, current graph, define graph settings, and you choose whatever you want to see. So see this total drag. So if you put it here, now see that, recall that we're using the method that is non-linear, that we have the viscous information coming from the airfoil that is linearly interpolated. So see that now we have CD0 and our polar here. Also, we're using the CD6 airfoil that have a drag bucket that you don't see here. So recall that we also talked that the induced drag is a very large component, and this very large component usually tends to hide that information of the airfoil. Okay, so if you want to see if you have that kind of drag bucket, you should look only at the viscous component. So you go back here again, define graph, you choose the viscous component, and see that kind of here you have your drag bucket. Okay, remember that here there are some interpolations at 3D wind, but here you have that information. But that induced drag is a very large component and usually tends to hide all that information. So it's up to you to pick out what you want to visualize. You have everything there. Okay, so in this case I like to put CD here. I have alpha gain CL. You can go also and plot, probably will make more sense to you, define graph, and you put alpha in function of lift force, which is F set. Okay, this is your lift force. Okay, and then see that here for 4 degrees you're producing this amount of lift. Somewhere we define the velocity. We're going to see that in the other, okay, when we do the setup from scratch of a wind. Okay, so basically here you have your velocity. So this is how the brief introduction of the case, just to recall what is the problem. So that's all for this video. In the next video, we're going to do everything from scratch. So we're going to design the wind, the platform of a rectangular wind. Okay, we're going to do the example that we were working in the class, this geometry. Okay, so thank you for your attention and see you in the next video. Bye.